Welcome back, everybody. This is Programming and Optimization with Intel Architecture, the hands-on workshop, and I'm Andrei Vladimirov. This is day 2 out of 10, and I will make a quick overview of the course information for those who have just joined us. This is the September 2015 run of the workshop, and we are now in day 2. In day 1, we talked about Intel parallel architectures and focused on Intel Xeon processors and Intel Xeon Phi coprocessors. This course has a page, and if you go to this page, you will find the slides that I'm using. So this is the page, and yesterday's presentation is already posted. So slides of yesterday's presentation and code of yesterday's presentation, and also the video recording of yesterday's presentation is posted. So if you missed yesterday's session, you can go here and watch it. Today's presentation doesn't obviously yet have a recording, but the slides are available and the code. This site, Colfax Research, requires registration, which is free and simple. And once you've registered, you will get access to all of the resources that we have here, including white papers with downloadable code and tutorials and video courses. This course is based on a book called Parallel Programming and Optimization with Intel Xeon Phi coprocessors. This is Colfax's original publication, 508 pages available as electronic or print. This is optional to have for the course, but if you want to get it, you will get printed information about all the topics that we are discussing. Actually, even more, because in the workshop we just don't have the time to go into all the topics. And all the code that we are dealing with in the hands-on part also comes from this book. We are providing remote access for the hands-on exercises. So yesterday I provided access to 56 people, and those people should have received an email message with connection instructions. If you have not received connection instructions yet, then you must be on the wait list. And the wait list is ordered by we will give first preference to people who show up to live presentations, and then order them in the order in which people registered. So the earlier you registered, the earlier the wait list will trickle down to you. And we are actually adding more seats, so I expect to go through the wait list pretty quickly so that most people will have a chance to do the hands-on exercises. If you attend 6 sessions out of 10, you will get a certificate of accomplishment in the fundamental level, meaning that you've attended the course and there was no post-training exam in this course. And one more resource for this course is colfaxresearch.com. As I mentioned, this is not just for the workshops. We have publications such as case studies, tutorials. We have slides of presentations. We have proper video courses on the site, and everything becomes available once you create a free account. Now I will do an overview of what happened yesterday so that we ease into today's topic. We are talking about Intel architecture, and Intel makes a lot of processors, most of which are actually parallel processors. They have multiple cores and they have data parallel support for data parallelism inside of every core. But we are focusing on just 2 platforms, Intel Xeon processors and Xeon Phi coprocessors. So we are not actually talking about desktop processors such as Intel Core, well, i3, i5, i7, but the processor that we're focusing on is the enterprise-grade Intel Xeon CPU. And we are also talking about a specialized processor called Intel Xeon Phi coprocessor. There are lots of similarities between them. Most importantly, you can run applications compiled from the same code on Xeon and on Xeon Phi. And yesterday we talked about the native programming model for doing just that, using the same exact code. But it is even more than reusing the code. If you parallelize your application using a framework such as OpenMP or MPI, or some of the popular threading frameworks such as TBB or pthreads or Silk Plus, the same parallel application will also run on the Xeon Phi coprocessor. This is possible because Xeon Phi is not just an accelerator. This is a proper processor running its own operating system. And also, it is architecturally similar to the Xeon. It has its own memory, high bandwidth GDDR5 memory, 16 gigabytes in size. And this memory is cached. It has the level 2 cache and the level 1 cache, just like the Xeon, except quantitatively Xeon has more memory and more cache per core. Xeon Phi has many cores, up to 61 active cores, clocked at 1 gigahertz, which is similar to the Xeon, which has up to 18 cores per socket, clocked at around 3 gigahertz. There is also each core represents itself as multiple logical processors. In Xeon, this is done using the hyperthreading technology with 2 hyperthreads per core. In Xeon Phi, this is done using by running 4 hardware threads per core. And another similarity, with again a quantitative difference, is that Xeon has support for vector processing inside of every core. Xeon Phi also has support for vector processing inside of every core, but Xeon Phi vectors are longer. And on the one hand, all of these quantitative differences mean that Xeon Phi can produce better performance than Xeon for, and I'm talking about performance per watt or performance per dollar of setup costs or performance to volume ratio. But on the other hand, the differences show that not every application will run well on Xeon Phi. The application must have enough parallelism and it must use memory efficiently. Only then will this application run well on Xeon Phi. But really the flip side of the story is that if you have an application that runs well on Xeon Phi, then the same exact code can run well on Xeon. Because Xeon Phi of the first generation is coprocessor, it has to have the host system. So this is a PCI Express endpoint device. You plug it into the PCI Express bus on the host, and then this device runs its own operating system. It has its own cores. It essentially operates independently, including having its own memory address space. So you cannot spawn multiple threads on the host and expect these threads to spill over to Xeon Phi magically. This doesn't happen because Xeon Phi has its own memory address space. And to program Xeon Phi, you have to use one of the programming models. One programming model that we discussed yesterday was native. Native programming means that the entire application starts on Xeon Phi and it keeps running on Xeon Phi without involving the host for anything other than administrative tasks such as handling networking or file I/O. Today, we're going to talk about another option for programming Xeon Phi, the offload programming model. And in all of our discussions, we focus on how to just run something on Xeon Phi and not necessarily in parallel and not necessarily optimally. In fact, starting from tomorrow, we will begin talking about parallelism. And once we start talking about parallelism, the discussion will become generic. We will not focus specifically on Xeon Phi. We will talk about parallelism generally in Intel architectures. But today's topic is how to run something on Xeon Phi in the offload programming model. The reason that you have these two programming models is that you can accommodate a variety of applications. Some applications just don't have parallelism. Well, one of such applications most of us use daily, and it is called a compiler. So compilers, compilation does not parallelize very well, except for compiling multiple files simultaneously, because compiling a single file is essentially a serial operation. But of course, there are some other applications that are computationally intensive and cannot be parallelized well. For these applications, you can execute multi-core hosted applications. In other words, run everything on the CPU. But some applications have these serial parts or parts with a lot of file I/O, but other parts in these applications are highly parallel. And this is when the offload model becomes useful, because you will run the application on the host and parts of it will be pushed over to the Xeon Phi. But there may be cases when the entire application is highly parallel. And then you can either use Xeon and Xeon Phi in a symmetric heterogeneous mode, where the same code runs on Xeon and on Xeon Phi, but they process different data sets. Or you can forget that you have the CPU and run everything on Xeon Phi. This is the many core hosted case. And the reason excuse me, the two programming models allow you to scale not just across multiple coprocessors within one system, but also across multiple coprocessors in a cluster. And with Xeon Phi, there's two ways that you can scale across a cluster. So this is my cluster. It has one compute node, another compute node, and each compute node has a CPU and one or many Xeon Phi coprocessors. So one of the ways to scale across this cluster with coprocessors is to use a framework such as MPI, Message Passing Interface. This is a parallel framework for distributed computing. And I will put one MPI process on every CPU. And then I will use the offload programming model, which we will discuss today, to push parts of the application to Xeon Phi coprocessors. Another way to program Xeon Phi coprocessors is in a cluster is to put MPI processes directly onto Xeon Phi. In this case, I don't need to use the offload. And there are pros and cons in each of the models, and I hope they will become clearer after today's presentation. So today we are talking about the offload programming model, and we will focus on one of the three available APIs, which is called explicit offload. And I will mention the other APIs for offload towards the end. So we will mainly talk about explicit offload. So this is a hello world application. This is probably the best way to start learning it. The application has the main function, and it begins execution on the host. At some point in my application, I will have a directive that looks like this: pragma offload target mic. And this directive has an opening parenthesis and the closing parenthesis. And between them, in the scope of this pragma, is arbitrary code. So this code, at compilation time, will be compiled for the Xeon Phi architecture. And at runtime, this pragma will cause communication between the application and the Xeon Phi driver. And at runtime, this compiled code will be transferred along with some data across the PCI Express bus to Xeon Phi. It will be executed on Xeon Phi, and then the results will be returned back. And as you can see, I have a closing parenthesis and then I print by, and this line will actually be executed on the host. So this is not a parallel application. There's no no talk about efficiency yet, but I'm showing this because it is easy to start learning, and then we will discuss all the bells and whistles that you can use with the offload model. To compile this application, I will call the Intel C++ compiler. It understands the offload API. Then I give it the name of the source file and the output executable file name. If you attended yesterday's class, we talked about native programming. And in the native programming model, we also use the argument -mmic. Here, I don't have any other arguments. In the offload programming model, I don't use -mmic. And to start the application, I don't need to do any of the stuff that we discussed yesterday. I don't have to copy the file to Xeon Phi. I don't have to SSH into Xeon Phi. I just run the application on the host, and it says hello world from host by hello world from coprocessor. So it is important to understand why the order of lines is not the same as in the original application. So in the original application, we had hello from host, hello from coprocessor by. When we ran, we had hello world from host by hello world from coprocessor. So this is um, uh, happening because the line hello world from coprocessor was printed into the standard console on Xeon Phi, and there is a functionality called console IO proxy, which buffers the output on Xeon Phi, and then it copies it back to the host. It is important to realize that this is not because the offload was asynchronous. In fact, offload is by default blocking. So when I reach this line, pragma offload target mic, I will begin the offload, and while offload is running, the host will be spinning. So control does not return to the host, does not return to line 8 until the execution on Xeon Phi has finished. But nevertheless, even though offload was blocking, the order of lines was different because there was buffering involved of the console IO on Xeon Phi. You already see that the code that we have in the scope of pragma offload is a standard code in C. And in fact, I should have noticed this, I should have mentioned this earlier. What I'm discussing as an illustration, I'm using code in C, or it will also compile as C++, but the same applies to Fortran. Fortran supports the offload model. The principle is the same. You have a directive. The syntax of the directive is different. Instead of a pragma, you have the keyword dec with a special character at the beginning. But everything that I'm discussing also applies to Fortran, just the syntax will be slightly different. So what you must have noticed is that inside of this pragma, I just have regular C, C++ code, or it could be Fortran code. So in principle, the same code could be run on the host CPU. And in fact, we can do that by including the keyword, by including the clause optional in this directive pragma offload target mic. So when I add the keyword optional, this is what will happen. The compiler will see this code and it will realize, this code may be run on Xeon Phi if the user has a Xeon Phi, but this code might be run on the CPU if there is no Xeon Phi in the system. So I am going to compile this code twice, once for the CPU and once for the coprocessor. So when I compile this code, nothing special seems to happen. When I run it, if I have a Xeon Phi coprocessor, offload will automatically occur, and as you can see from the number of the logical processors, the code ran on Xeon Phi. Now I could go and pull the Xeon Phi coprocessor out of my system. Well, that would be a drastic measure. So I used a less drastic measure, which still is overkill, but it works. I stopped the MPSS service. Remember, yesterday we talked about MPSS, the Many-Core Platform Software Stack. This is the service runs the driver of the coprocessor and the communication with Xeon Phi. When I run the application after that, Xeon Phi is not accessible. So at runtime, the application realizes there's no Xeon Phi, so I will use, in the scope of this pragma, code compiled for the CPU, and the application seamlessly falls back to the CPU and runs there. You can already see that I'm dealing with a number of logical processors here, and I want to point out something important for future discussions. When you have offload, how do you handle multiple cores on Xeon Phi? Do you run 244 offloads, or do you do something else? Well, the answer is do something else, and that is when you have an offload region, you must have a parallel application inside of it. So this is different if you're, for example, if you are used to programming GPUs, you would design kernels, which are essentially serial functions, and then you would make special calls that indicate how to parallelize the dataset across these serial functions. With Xeon Phi, it is different. The code that you design for Xeon Phi, the offloaded code, must be a parallel code, and how to make it parallel we will talk about later. So the code snippets that I showed were very clean and really exciting. It is that easy to run something on Xeon Phi. And of course, this is only easy while the code is relatively simple. And the code is relatively simple as long as you don't offload functions or data. So now let me talk about what happens when you start offloading functions. Well, you remember that when I include the keyword optional, the compiler will have to compile the code in the scope twice, once for Xeon and once for Xeon Phi. And even if I don't have this keyword optional, the compiler must know ahead of time that this function must be compiled for the Xeon Phi architecture. So to give the compiler this hint, you have to include this statement, attribute target mic, before the function declaration. When the compiler sees this function, it will realize, I need to compile this function for the Xeon Phi architecture. Or even better, I will compile it twice, once for the CPU and once for the Xeon Phi architecture, so that I can use this function in an offload region, which can be an optional offload region. So this is necessary when you declare functions, and of course this doesn't look very pleasing to the eye, and it will be difficult to do it if you have many functions in your code. So there is a shortcut. The shortcut is another pragma. This time this is pragma offload attribute push, and then it has the argument target mic. This pragma tells the compiler that all objects starting from this line must be marked for offload. So this function will be compiled for offload. This function will be compiled for offload. And finally, I will end this special code region with pragma offload attribute pop. This is useful, for example, when you want to put an include statement here so that you declare all objects in a header file for as offloadable. When you are dealing with data, sometimes you don't have to do anything. I have a function that declares a scalar, and it declares a scope local array. And because the compiler knows at compilation time the type of this variable, the type and the length of this array, it will automatically stage the transfer of data to Xeon Phi and from Xeon Phi when I run this code. So what exactly is going to happen? When I reach pragma offload target mic, the compiler will recognize I'm using n and data on Xeon Phi. So I will have to create a buffer to hold n. I will have to allocate a buffer to hold data. And I will have to copy everything from the host to Xeon Phi into these buffers at the beginning of offload. Then data was modified on Xeon Phi, so the compiler will copy the modifications back to the host at the end of the offload, and it will deallocate the buffers for data. This works magically, and this is limited to bitwise copyable data. It works automatically doesn't mean that it's always good for performance. I will actually show you how to tune performance for operations like that in a minute. But it is important to realize that if you have C++ classes or any complex objects inside of the offload region, they will not be automatically copied. This is only for bitwise copyable data. If you are using data that is not scope local, but global or static, you also have to tell the compiler ahead of time that this data is going to be used on Z1.5. So this pointer-based array I declare with attribute target mic, and this static variable I also declare with attribute target mic, and of course I can use a float attribute push pop if I want to. Now, this is enough to just allow the code to compile. But when the data is pointer-based, or in Fortran when you have allocatable arrays, this is not enough. And this is when the fun starts. So now imagine that I have two pointer-based variables, and I allocate them on the heap using the allocator malloc. So this is C or C++, or in C++ I could use new. In Fortran, the equivalent of that is using allocatable arrays. So if I do that, the compiler has a problem. It no longer knows how much data is hiding behind this pointer-based array, or how long the allocatable array is. To make the application run correctly, I have to do what's called data marshalling. And data marshalling can be done with these two, clauses in, out, and no copy. I add them in the pragma, and this is what it means. In P1 length n means that before the offload, I want to copy all the data from the host, hiding behind the pointer P1, and I want to copy n element. Notice that this is not bytes, but elements. And I'm copying in, meaning from the host to Z1.5. Out means the opposite. At the end of the offload, I will copy all results from Z1.5 back to the host, and the length of the results is n. Data marshalling is required for pointer-based variables, but it is also optional to use data marshalling in cases like this, when the compiler could do it for you. But sometimes you may save some time by not copying data which is persistent. And I will have a few slides about that. So before we move on to the next topic, I want to address some of the questions that came in. And one of the questions that was asked has to do with with a container from the C standard library. The question is there a way to make it work with an std vector double or a customized vector container? So this container is a C++ class in the C standard library, and there is some data hiding behind this array. So if you try to offload data hiding behind that pointer to an std vector, it will not compile because data marshalling is only for pointer-based variables. But it doesn't mean that when you have standard C library containers, you cannot use offload. You can, and there's two ways to do it. One is you can create a temporary container, which is a plain array, and you can copy all the data from the vector to that array and then offload it. Actually, the copying of data is around 10 times as fast as the offloading. So the overhead for doing that is not great. Another way to do that, another way to work with vectors or val arrays is to use another API for offload called the virtual shared memory model. And I will talk about this later. And also before I go, I'm talking about the pragma offload. I'm talking about the explicit offload model, and the API that I'm talking about with pragma offload is called LEO, Language Extensions for Offload. This is Intel proprietary syntax, and this is also Intel proprietary syntax and This is also Intel proprietary syntax, and this is supported only by the Intel compiler. Later, I will mention another approach to explicit offload, which is offload in OpenMP 4.0. And this is actually a standard which could be supported by other compilers. As of today, I am not aware of other compilers supporting it, but um, I will point out an API which can be portable, and this addresses, yeah, the reason I'm talking about this is I'm addressing another question. And finally, one more question came in, was how will there be differences for KNL, for instance, attribute or push-pop method? So the question is about the second generation of Xeon Phi coprocessors. And the second generation of Xeon Phi coprocessors will be available in two form factors, as I mentioned yesterday, a coprocessor and a socket version. So for the coprocessor, I would expect that everything will stay the same. For the socket version, you wouldn't probably want to use offload, and you would just use the native programming model as we discussed yesterday. And this is as much as I can talk about it as of today, I guess. Hopefully that addresses the question. So let's go back to this subject and discuss something more advanced. Some systems have multiple coprocessors. How do you use multiple coprocessors with explicit offload? There's two parts to this problem. One is how to specify which coprocessor you want to use, and the other part is how do you use them concurrently. So first, let's deal with how to specify the coprocessor. You can query how many coprocessors you have by running this support function, offload number of devices. It returns the number 0, 1, 2, 3, however many coprocessors you have available in the system. And then if you want to offload to coprocessor number 0, you say pragma offload target mic colon 0. If you want to offload to coprocessor number 1, you go colon 1. And if you actually shoot over the number of the coprocessor, so you have two coprocessors and you specify 99 here, this is still fine because the enumeration loops over. So if you have two coprocessors, then 0 and 1 is the same as 2 and 3, same as 4 and 5, and so on. If you are inside of the offload region, you can call another support function called offload get device number. And this function returns the number of the coprocessor on which you are running. By the way, when you don't specify the number of the coprocessor, then the system will alternate between offloading to 1, to the first, second, third, and so on at runtime. Another issue with using multiple Xeon Phi coprocessors is how to use them in parallel. As I mentioned, offload is by default blocking. So when I start offload to coprocessor 0, I will not be able to start offload to coprocessor 1 until this offload finishes. The best way to use multiple coprocessors in this case is to dedicate one host thread to every Xeon Phi. I have another statement here that reads pragma OMP parallel num threads and devices, where n devices is the number of devices. I will talk about this in session number 4. This is a statement from the OpenMP parallel framework. A similar statement can be used in Fortran. What it does is it creates multiple threads on the host. And everything inside the scope of that pragma is executed concurrently in different threads. Threads are enumerated. I can get the thread number 0, 1, 2, 3, 4, and I can map the thread number to the coprocessor number. So offload will still be blocking, but each offload will only block its own thread. All other threads will run simultaneously. If you remember, I showed a system in the previous course with 8 Xeon Phi coprocessors. This is one of the systems that Colfax makes, and This is how you would go about using 8 coprocessors in that system. You would dedicate 8 threads on the host, and each thread will offload to its own Xeon Phi. When you do data marshalling, you have some control that allows you to improve performance in certain situations. This control comes in the form of specifiers alloc if and free if, and they allow you to have memory buffer retention and to have persistent data on coprocessors. So we are all here to improve application performance, and if you want to improve performance, probably your application runs long enough, which means that likely you will be doing more than one offload in the application. Oftentimes, those multiple offloads will have to use the same data. Some data will be different in different offloads, but other data will be the same. For example, if you're dealing with a physics application, you may have some physics data tables which you want to offload to Xeon Phi just once and keep them there. This is when you need persistent data on coprocessor. You make one offload, you offload the data, and then next time you do the offload, the data is already there. Another case where you need these clauses is when you don't reuse the data, but you want to reuse the space allocated on Xeon Phi. And this is very important. As I mentioned, by default, when offload occurs, the system will allocate a buffer for data on Xeon Phi, copy the data from the host to Xeon Phi, then run the offload. And at the end, it will deallocate data. At the end, it will copy the data back to the host, deallocate the memory buffer, and return control to the host. The catch is that the sending of data is actually fast compared to the allocation of memory buffers. When you send data across the PCI Express bus, you achieve 7 to 8 gigabytes per second. But if you are allocating a large memory buffer on Xeon Phi, in the first generation of Xeon Phi at least, you get anywhere between half a gigabyte per second and 2 gigabytes per second. So memory allocation will actually take most of the time. How do you work around that? Here's a few examples to illustrate what you can do. Suppose I have data sitting behind the pointer P, and I have n elements in this array. I'm offloading to coprocessor 0 and data elements, and then I include two specifiers, alloc if 1 and free if 0. So alloc if 1 says that I only want to allocate a memory buffer on Xeon Phi for this data if the expression in the parentheses evaluates to true. So this, in my case, is an integer, but it could be an expression that evaluates to 0 or 1 or true or false. And in this case, I will allocate a memory buffer for my data. Free if controls what's happening at the end of the offload. Do I free this memory buffer or not? And the syntax is maybe a little bit confusing, but it will only deallocate the buffer if this expression in the parentheses evaluates to 1 or to true. In this case, I have a 0, so it will not deallocate the memory buffer. So what I'm doing is I'm allocating the buffer, transferring the data in, and then after the end of the offload, I return and I keep the data along with the buffer on Xeon Phi. Next time, if I want to go in and reuse the memory buffer and avoid this overhead of allocation, I will go in length n alloc if 0, meaning do not allocate, reuse, and then free if 0, meaning keep. Or I could reuse not just the buffer, but also the data. I will go in p length 0. So I will make this pointer p available in Xeon but I will not copy any data, and I will not allocate a buffer, I will not destroy the buffer, and at the end, if I want to be nice, I will go and deallocate the buffer on Xeon this is necessary to avoid memory leaks, but if you forget to deallocate your buffers, and when you terminate the offload application, memory will be cleaned up automatically. With persistent data, often the practical story is that people start doing that and then they have runtime errors and they're trying to figure out what happened. One common error is forgetting to specify the coprocessor number when you have multiple coprocessors. As I mentioned earlier, if you just have target mic and you don't have target mic 0, then at runtime the system will alternate between the coprocessors that it uses. So you might allocate a buffer on Xeon Phi 0, and then you will try to reuse it on Xeon Phi number 1. This is not going to work. Another issue that people have very often is the value of the pointer. The key is you should not change the value of this pointer between successive offloads. And here's why. When I offload this pointer-based array P, how does the runtime system know which buffer on Xeon Phi this corresponds to? It actually doesn't go by the variable name. Rather, it goes by the memory address to which P is pointing. So there is a table in the memory of the runtime offload library, and this table has a mapping between offloaded host side pointers and Xeon Phi side pointers. If you change the value of the pointer, you will not locate the key in that table, and you will have a runtime error. It is actually good that the compiler doesn't go by the pointer name but goes by the pointer value, because you can do offload from one function and then you can start another function and reuse the data on Xeon Phi using the same pointer value. We started talking a little bit about optimizing the offload traffic, and it is important to retain memory buffers and data when you can. Another important aspect of communication optimization is overlapping communication with computation. Earlier, I said that offload is blocking by default, so now is the time to clarify how to make it non-blocking or asynchronous. When I start the offload, I can include the clause signal, and it takes an argument. This argument is essentially the identifier of the signal. And this identifier basically has to be a 64-bit unique value. It is very convenient to pass a pointer, ideally the pointer to your data as the signal. And when you do that, offload will begin, but control will immediately return to the host. And the host may do something else, maybe stage the next offload or run computations on its share of the data in a symmetric mode. But then eventually you will want to synchronize with the offload, and the barrier for synchronization you can run with the pragma that reads pragma offload wait, and then you give it the target from which you await the offload, and you give it the clause wait and pass the same identifier as you used here. The way that it could work, for example, is double buffering. Double buffering is a technique for masking communication and computation when you have a batch calculation. So suppose I have many data sets and I want to run some sort of a computation on each of the data sets. For specificity, let's imagine that I have sets of matrices A and B, and I'm trying to run dgem double precision general matrix multiplication on these matrices and obtain the results. So I could naively just transfer the data in, run calculation, transfer results out, transfer results in, computation results out, and so on for many data sets. So the x-axis is time. With asynchronous, that would be with blocking offload. Now with asynchronous offload, I could do something like double buffering, where I have two buffers on Xeon Phi to hold two data sets. So first I will stage in the first data set, and starting from that point, I will start overlapping communication with computation. I transfer the first data set in, and then I start computation on this data set, but I do it asynchronously. So control immediately returns to the host, and the host starts staging in the next data set in the second buffer. When the computation is done, I will start computation on the next dataset, but I will do it asynchronously. Control will return to the host, and the host will fetch the result of the calculation and stage in the next dataset. This is called double buffering because I have to alternate between the two buffers as I go. The code for this may look complicated, but conceptually it is simple. I have a loop that goes over all my datasets. I begin offload. This offload is asynchronous because I use the close signal. You can see that I'm also using specifiers to control data reuse and memory buffer retention. I start my computation, but this offload is asynchronous, so immediately I go here and I call pragma offload transfer, which is the same as pragma offload without any code. And this stages in the next dataset, fetches the results back, and then uses offload wait to synchronize with the offload. And then I will have to swap between the two buffers. This code you can find in our book or in the labs on your remote training server in one of the chapter 2 exercises. So when you do offload with memory retention, asynchronous offload, maybe multiple threads, things can get complicated quickly. And to help you troubleshoot what's happening, you have some additional offload controls, which I will discuss now. One control useful for offload, but also useful for the native programming model, is the preprocessor macro mic. So it's actually underscore underscore mic underscore underscore. Preprocessor macro is something that's usually very familiar to C programmers and C++ programmers. It also can be used in Fortran, even though it is not common practice, but you can do that. What's the meaning of this pragma? Well, I have a function which is declared as offloadable. So the compiler will compile this function twice, once for the host and once for the Xeon Phi. So when the compiler is doing the Xeon Phi compilation, this macro is defined. So a preprocessor statement like that will make sure that this code is compiled for Xeon Phi, but that code is not compiled for the Xeon Phi. In the second pass, when I'm compiling for the host CPU, the macro is undefined, so this will not be compiled, but lines 6 and 7 will be compiled. I can use this to write target-specific code. For example, I can tweak the output that I'm printing out, or I can tweak the values of the tuning parameters. This, for instance, allows you to control, do I have the offload, and depending on that, print some diagnostic statements. Now, another diagnostic that you can generate with the offload model is built in. You can set the environment variable offload report to 0, 1, 2, 3, and when you run the application, it will run normally, but automatically the runtime offload library will produce output like this, which reads offload to this target in this file, that line. This is how long it took. This is how much data was transferred, and so on. I want to point out something important here. You can see that we did an offload, we transferred 1 kilobyte of data to Xeon Phi, and it took, wow, half a second. Does it mean that it is that slow? No, it actually is very important to point this out, but this was the first offload. The first offload is always slow because this is when you initialize the coprocessor side of the application, and sometimes during the first offload there is some paging, creation of virtual memory pages going on Xeon Phi. So the first offload is always slow, and when you do any kind of benchmarking, don't rely on the first offload. Ignore the first offload and only measure sustained performance in the second, third, and so on offloads. So back to offload controls. Another environment variable for offload control is offload devices. This variable allows you to restrict which coprocessors you allow your application to use. If you set it to none, then you will prevent offload completely, and this is useful for testing. If you set it to a comma-separated list, then you can only offload to these devices. And 0, 1 means that you can offload to devices number 0 and 1. This is useful, for example, when you want to partition your system between multiple processes, or maybe even between different users. So you give one Xeon Phi to every user, and you just coordinate it between them by setting this environment variable for them. Of course, this is not a secure way to do it by any means, but it is easy to set up. As you can see here, I have an offload application with fallback, and I'm doing a non-drastic measure to disable coprocessors. So first time I run it, I have a Xeon Phi. It reports 244 logical processors. The second time I run it, I set offload devices to none. It disables offload, and the code falls back to the execution on the CPU. With environment variables, when you do offload, the default behavior is that all environment variables on the host are copied exactly to Xeon Phi, with one exception. LD library path is not copied over. So sometimes this is a good behavior because you just set environment variables on the host, and these environment variables help your application on Xeon Phi. But other times you may want to have different values for one environment variable on the host and on Xeon Phi. For example, this variable, we will discuss it on Monday in the section about OpenMP. This variable controls how many threads I want to run in my application. And this is usually chosen as the number of logical processors or physical cores in your system. So for the host, in my case, I have a host with 24 physical cores. I set this to 48. But if I just do that, then on Xeon Phi, I will also run with only 48 threads instead of 240. So to disentangle the host value and the Xeon Phi value, I use this special variable. This is the offload control. mic_env prefix. I can set it to any string, and when I do that, variables whose names begin with this string will be treated specially. So this variable, at runtime, the library will copy this variable to Xeon Phi, and then it will drop the prefix. So on Xeon Phi, I will have OMP num threads equals to 240. Regarding the offload programming model, as I said, there are 3 APIs, and the one that I discussed was called explicit offload with Leo, language extensions for offload. This is an Intel specific syntax. It is only supported by the Intel compiler. In fact, I don't know of other compilers that support offload as of today, but in the future, offload may be added to other compilers, and this is where other APIs for offload may come in useful. Specifically, there is a specification for OpenMP version 4.0, which has some controls for offload. We do not have practical exercises on this, but I want to show this to you so that you know what you're dealing with when you see it in other people's code, or if you want to use it, you can look up the complete syntax in the compiler reference. So what I'm showing now is still offload, but with a different syntax. This syntax is designed to be portable, and potentially you can use it on in different compilers, even supposedly for other platforms such as GPUs. This syntax doesn't have pragma offload. Instead, it has pragma OMP target, and it allows you to express basically the same thing. Pragma OMP target means that whatever you have in the scope of this pragma will be copied over to Xeon and executed there. With the Intel compiler, the back end for this type of offload is exactly the same as the back end for pragma offload. It is the syntax that is different. And actually, this syntax, as I will show, has some limitations as of today, but they may be lifted later. With this pragma OMP target, you can specify the device to which you offload. You can specify a mapping. This is the equivalent of in, out, in, out. You can make the offload optional, and if you download the slides, click this link, it will lead you to the manual page with complete syntax. So the difference between pragma OMP target and pragma offload is how you work with persistent data. With pragma OMP target, at least in the past, you used to have to create a scope, such as pragma OMP target data map, and then in the scope you specify that you want data to be copied out of the Xeon Phi, and then you run one offload. Then potentially here I could have some lines that run on the CPU, and then I run another offload. But between these offloads, the data hiding behind this pointer will be retained. I can also update the data between the offloads using pragma OMP target update. And when I declare, and of course, what I showed is only clean when I don't transfer functions. When I transfer functions, I have to declare these functions as offloadable. And the syntax is pragma OMP declare target. And then I will have to end this region with pragma OMP end declare target. So this is the equivalent of pragma attribute target push. This is the equivalent of pragma attribute target pop, but it works with the OpenMP 4.0 API. And again, completely syntax you can look up in the manual. It is important to realize that these are different interfaces to the same offload library backend. Pragma offload target is Intel specific. Pragma OMP target is a part of a cross-platform standard of OMP 4.0, and we will see in the future how well adopted this support will be. Last check, pragma offload target only allows data persistence. Pragma offload target allows memory persistence outside the scope of the pragma, so you do offload from one function and reuse in another function. But pragma OMP target only within a lexically structured scope. We've been promised that it will be changed in Parallel Studio 2016. This edition is out now, but to be honest, I just haven't had a minute to check, so this may be different in the latest compiler edition. And before we move on to the practical part, I want to discuss in 2 slides yet a third API for offload, the shared virtual memory offload model. In this model, you only have 2 keywords, silk shared and silk offload. Silk shared is a declaration that says that this object or this function may be used in offload. Silk offload, followed by the function name, initially initiates the offload. The difference here is that the shared virtual memory model allows you to share complex objects. Your own classes or any kind of containers, you can seamlessly share them with the Xeon Phi. But this is virtual shared memory model because in fact, in reality, there is no sharing. Data is copied still from the host to Xeon Phi. In this model, there is no control for data marshalling. You don't get to specify which data goes where and when. Instead, the runtime system does it for you. It monitors all memory pages in the shared memory model, and the pages that were marked dirty, that were modified, will be automatically synchronized before and after the offload. It is important to notice one aspect here. When you allocate pointer-based arrays for this memory model, you have to use a special allocator, offload shared malloc, and it returns a pointer that has the same value on the host and on Xeon Having the same value of the pointer allows you to share arbitrarily complex structures such as trees, linked lists, or any other kinds of pointer-based structures. This is not supported in Fortran. This is only for C++, and you can also compile it in C. I will demonstrate a practical exercise on this topic in the second hour. But for today, I want to wrap it up with a summary and also announce what's happening tomorrow. So today we talked about offload programming. And my main focus was the explicit offload model with the language extensions for offload API, Pragma offload. But you can also do explicit offload with Pragma on ptarget. This is when you essentially start your application on the host. Then you have a directive like Pragma offload, and this directive causes a part of the code to be run on Xeon Phi. I also mentioned there is a shared virtual memory model that allows you to share arbitrarily complex pointer-based structures. But it is important to also realize that offload is only one of the ways to program Xeon Phi. In session 1, we talked about programming Xeon Phi with the native programming model when you run the entire application on the host. So we will soon move to the hands-on part. For tomorrow, I want to announce the next topic. We will start talking about parallelism, and first we will discuss data parallelism and vectorization. Our discussion will become generic. We will not talk specifically about Xeon or Xeon Phi. It will be applicable to a variety of platforms. So let's now make a 2-minute break. If during this break you come up with any questions, please type them in the question box and I will address them at the beginning. Also, during this break, please connect to your training servers if you have connection. If you don't have connection, then stay on the line because you will be able to follow along with me, and I think it's a good way to learn. So see you in 2 minutes. Stay online. So I am ready to resume, and I connected to a different system, but it is I'm still using the same remote desktop as I recommended to you. So I will go here and do full screen. Yep. So hopefully everybody who has remote connectivity was able to connect. If you have any issues, please send me an email. Just respond to the message that invited you to join. And let's begin. So a reminder, we have the directory called labs. And inside of this directory, there's 2, 3, 4, 5. These correspond to different chapters in our book. And I will now go to chapter 2. Chapter 2 talks about programming models. In other words, how to run something on Xeon Phi without concern for um, parallelism or performance. We will start talking about parallelism in the next session, and we will start talking about performance starting from session number 5. So today I will go to lab 203, and let's see what I have here. The structure of the lab is usual. I have the code that we will be dealing with. Here now I have a make file, and I will talk in a second about what it can do for you. But also it has instructions txt. This is what you can open in your favorite text editor. These instructions guide you through what you're supposed to do in this lab to learn what we intended. And you can follow these instructions, but you can also go and look up the answer in the folder called solutions. Now the make file is interesting. In this case, it just helps you to compile the code. But we will see in other labs that the make file also has a target to execute the application. And this we will start using soon. So let me go to the instructions. I will not really go through them because I remember more or less what instructions are asking for. So I will just switch to the code and let's see what we can do to learn. This code allocates a matrix and 2 vectors, and then it runs matrix vector multiplication. It actually does it several times, and for every run it uses a different vector. So this is not a particularly meaningful application, but this is a good playground to learn how to do offload. So first let me compile and run it. As you can see, I used the Intel C++ compiler, and I will be using the Intel C++ compiler in all of the exercises because as of today this is the only compiler that supports compilation for the Xeon Phi architecture, and the pragmas that I talked about earlier, the offload pragma, is also just for the Intel C++ compiler. So if you don't have it, you can download if you don't have it, if you are using your own system and you don't have the Intel compiler, you can download a trial version for free. It's valid for 30 days, so you can use it during the training. So I compiled the application. As you can see, I did not use the argument -mmic. I used the argument -g to include the debugging symbols. And the executable is called runme. So here's what happens. Running the matrix vector multiplication, checking the results, and we're good. So let's see, first of all, is it running on Xeon or on Xeon Phi? There seems to be nothing related to Xeon Phi here, so I would assume that it's just Xeon. And let's see what we have to do to run this on Xeon Phi. So what do we want to offload? We could potentially offload the entire matrix A and vector B. That wouldn't be particularly useful because I will be doing n squared calculation on n squared data. We will discuss that this is not a very useful case for offload. But if I offload matrix A and retain it there, and then I offload different values of B and fetch different values of C, then I should be fine. So let's try that. So I will just offload this statement, pragma offload target mic, and I will put curly brackets to indicate which part of the code I want to offload. So this might just work or it might not work. We will know in a minute. I will just run make, and the compiler complains. It says, error. Pointer variable A in this offload region must be specified in an in, out, or no copy clause. So what is happening? I have a region which is supposed to run on Xeon Phi. This region uses vector C and vector B. It also uses matrix A. So vectors B and C are scope local arrays of known size. Matrix A is also scope local, but it is pointer based. In Fortran, that is an equivalent of an allocatable array. So the compiler has a good idea of how to copy C and B into the coprocessor, but it doesn't know how much to copy for matrix A. So I have to include a clause that reads like this: in A colon length n times m. So why did I put in? That's because I want to take matrix A, which is initialized on the host, and I want to copy it into the coprocessor. Why do I specify n times m? Because this is how many elements it contains. Notice that I specify elements and not bytes. And now I can save and run. And when I run, the code compiles. So now let's see what happens when I run it. You can see that there is a visible lag when I run it. And this lag is associated with waking up the coprocessor and initializing the driver. But then I get the report that results are correct. So to prove to myself that I am really running on the coprocessor, I can run something like this. Let's see. Watch n1 mic smc-c. Let's see if it works. This seems to work. So mic smc is a performance monitor for Xeon Phi. It has a graphical version, but because some of you are connecting with a terminal, I'm demonstrating how to run it in a text mode. So once again, what I ran is watch-n1 and then in parentheses, in quotes, mic smc-c. So mic smc-c prints out this information. Mic 0, core number 1 has this utilization, core number 2 has that utilization. And as you can see, Xeon Phi is not doing anything now. And I'm running this command once every second to get updates as I go. So now let's run the code. And the code, I didn't notice what happened. Yeah, so I didn't really even see much utilization here because this is a very short duration run. So to make it slightly longer, let's see if I can make the matrix bigger. I run make. So I changed m to 100, I run make, and then I run me. I should be watching, yeah. Yeah, so I see a little bit of utilization here, really tiny in one core, and even that core I'm not using very effectively, but at least I get the correct result. So we succeeded in running something on Xeon Phi in the offload mode, but now let's see if we can run something more complex in this model. So I will go back to the code, and I want to see what happens if I want to abstract things out. Suppose instead of calling this code, I want to call a function, and function will be called my matrix vector multiply, and as input it will take A and B, as output it will have C, and it will also take the values of N and M, and this entire code will go into this function. So I have to, of course, specify the types of these arguments. So A is double pointer, this is double pointer, this is double pointer, and this is int, and this is int. I'm not doing it in the most um, I'm not really using good programming practices here, but this will at least work. So let me try to compile. When I compile, oh, this is not C. Yes, now the compiler says function my vector matrix vector multiply called in the offload region must have been declared with a compatible target attribute. So what happened? The compiler compiled this function for the host. It had no clue that I was going to do anything on Xeon Phi. And then it finds that I'm trying to call this function in the offload region. Well, too late, says the compiler. I don't have a Xeon Phi implementation. You should have told me sooner. So to tell the compiler sooner, I will go and insert the Intel specific attribute target mic. A lot of parentheses, and well, this is how it works. Now the code compiles, and when I run it, I see utilization on Xeon Phi in just one core because we have a serial code, and the results are correct. I can't say I'm crazy about the looks of this attribute, so let me implement the alternative syntax, which is pragma offload target offload attribute push target mic, and then I will have at the end of the offloadable region pragma offload attribute pop. So the code still compiles and it still runs. Okay, so I was able to run an offload application with a function. Now what about having global variables? Suppose this pointer A is going to be global. Then I don't have to pass it here, and I just initialize it here. And that seems like a good way to do it. But when I run the code, the compiler complains again. The variable has not been declared with the compatible target attribute. And that is because here I am trying to use pointer-based variable a inside of the offload region, actually here as well. But the compiler tells me too late, I'm not ready to treat this pointer as potentially being on Xeon Phi. You should have told me sooner. So what I will do is I will move the declaration of this pointer inside of this special region that makes everything offloadable. So now I can run make, and it runs. As I mentioned earlier, the real power of this approach is that I can have the same exact code in this matrix vector in this function, regardless of whether I intended to run on the host or on Xeon Phi. To prove this to you, let's experiment with this. I have at my disposal an environment variable, offload devices, and I can set it to 0. And this will allow me to offload only to coprocessor 0. Essentially, nothing will change. The code still runs. But if I set it to none, then things will change. At runtime, I get an error. Cannot offload to mic. Device is not available. So I am mimicking the situation where I don't have a Xeon Phi in my system. As you can see, the application fails. But to make it run, I can include the clause optional in my offload pragma. So I will have to save. I will have to recompile. And now when I run, you can see that the calculation was quick because I didn't have to initialize the Xeon Phi driver. Basically, I fell back to the host. And if I re-enable offload, I set offload devices to 0, meaning device number 0 is allowed. Then when I run it, it still runs on Xeon Phi. So I did not have to change my code, and it still runs. Now, how do I convince myself, besides looking at the runtime, that I was indeed executing on the host or on Xeon Phi? For this, I will use the preprocessor macro. And the macro reads underscore underscore mic underscore underscore. And if this macro is defined, it means that I am compiling for the Xeon Phi. And here I will do a print statement. And I will also prove to you that I'm running on Xeon Phi by including, actually no, let's not do that. I think that's enough. So I'm running on Xeon Phi. Otherwise, if I'm compiling for the host, I will print falling back to CPU. So when I recompile, let me try it again, recompile, I run, and it says running on Xeon Phi. As you can see, this was printed at the very end because it was buffered. So if I now set offload devices to none, and I run, falling back to CPU. Another control that I want to exercise here is offload report. So let me re-enable offload. And I will set offload report first to 0. And when I run, excuse me, I should have set it to 1. And when I run, it automatically produces an output like this. This file in this line with this tag performed offload, and this is how long it took. I can set it I can set the offload report value to 2 and verbosity will increase. Now I also have reports on how much data I was sending. And I also can increase verbosity to 3. And you can see that I get even more verbosity. I get pointer values and some additional diagnostic output. So this happens without my involvement, and this is a really easy way to troubleshoot what's happening. So what else can I extract out of this application? Let's experiment with offload report 2, 1. And let's focus on the amount of, actually no, we will have to use 2. Let's look at what's happening. In every, and let me change some values in my code so it's clear what's happening. So I will change it from 10 to, I don't know, 50. M, I will change to 50. Otherwise, we will have to count zeros. Okay, there we go. So for every offload, what's happening is this many bytes is sent to the Xeon Phi, and this many bytes is returned from the Xeon Phi. Now, what does this amount to? This many bytes is how long my vectors C and B are. This many bytes is the sum of matrix A, vector B, and C. I believe that's what I'm dealing with. Do I need all this traffic? I would think not, because the matrix that I use on Xeon Phi is always the same. So I can really save some time by retaining this matrix on Xeon Phi. And this is what I will exercise. So I have this statement in length nm. So in every offload, I require that this many bytes will be transferred. And for every offload, by default, the runtime library will allocate a buffer for matrix A, and it will before the offload. And at the end of the offload, it will deallocate this buffer. And as I mentioned, it is bad enough to send the data into Xeon Phi in terms of performance, because you're dealing with a PCI Express bus. But it is even worse to be allocating data. It is a very slow operation because Xeon Phi cores are low clock speed, and memory allocation is a sequential operation. So let's try to optimize it. I will add more instructions to the compiler. One of the instructions I will add is this: allocate if, and I will allocate if only the iteration is equal to 0. So I will only allocate upon the first iteration, and I will free if iteration equals max iter minus 1. So I'll deallocate on the last iteration. As you can see, the code is now getting ugly because this pragma is long. So let me show you how to do line breaks in the pragma. I have to put the backslash and then enter. If I have no more characters after the backslash, then this is going to be the continuation of this line. So let me also do a line break here. So this is all one pragma. The continuation character for Fortran is, I believe, different, but I don't remember it off the top of my head. So let's see what happens. I will recompile, run. I don't really see a big, well, I see a tiny change in performance. I used to have 0.55 seconds. Now I have 0.50 seconds. And this is actually because I'm also allocating and deallocating memory for B and C. So let's do the same for B and C. So B, C, B has length N, C has length M. But I also, well, let's try that. and I hope that I will get an error. Yes, I'm getting an error because I'm specifying the length of B and C, but B and C have known lengths. They are allocated on the stack, so the compiler doesn't like it. It will only allow me to specify length if I am dealing with a pointer-based variable like A. So I have to remove this, but I think I can retain alloc if and free if. And I will try to run it, and I hope to get an error now. Yes, I got the error. Something is wrong. The norm is incorrect. That's because I did my copying and pasting, and I forgot that vector C is actually the result, the output. So I don't have to send it in, but I have to send it out. And if I do that, I will still get an error related to the logic of this application. But the principle that I'm illustrating is the same. No, this actually worked. I would, because I'm actually accumulating in vector C. Let's do, well, as long as it works, let's keep it. So now let's see it. Let's look at what's happening. I had a lot of savings here. So because I specified that I don't want to deallocate buffers for B and C between offloads, and that saved me some performance that will save me some performance down the line. But a byproduct of this is that I specified that B is only going in, and it's going in every time. C is going out, and it's going out every time. So notice that what I'm doing is I'm retaining the buffers for B and C, but I'm not retaining the data in A or B or C. The data is always copied. A is always copied in every offload. B, I did not specify the length. I couldn't, but the compiler always wants to copy the entire vector B. It always wants to copy the entire vector C. But a byproduct of what I did is that out, I'm only copying 400 bytes instead of that many bytes. Well, I used to copy B and C out, but now I'm copying just C. This is why I only have 400 bytes here. So this is not bad. I know that I'm not wasting my bandwidth, but still, do I need to transfer that many bytes every time? The biggest problem is matrix A. The matrix A is the biggest container. It has dimensions n times m, and I am transferring it in every time. How do I work around that? How do I transfer it only on the first iteration? The trick that I like is this. I will define A bytes, and then I will have if iteration is 0, then A bytes, well, actually A copy. Then A copy will be n times m, otherwise A copy will be 0, and I will use this A copy here. So only on the first iteration will I transfer the entire matrix A, but in all subsequent iterations I will only transfer 0 bytes. And I will reuse the data because I retained the buffer for A and B. So now what's happening? Now what's happening is in the first offload, which is long, I'm transferring the entire matrix A. But starting from the second offload, I'm only transferring B. By the way, these 32 bytes come from the fact that I need to transfer some of the pointers. So I need to transfer the values of B, C, and an M in every offload. I think that's it. So I'm now economical with my um, data traffic. I did not see really a performance increase because I'm actually now dominated by how fast I can run the application. Uh, to show you something really cool and motivate you to come back to the discussion of OpenMP, I will put pragma OMP parallel 4 here, and I will also change the make file. And in the make file, I will use the argument qopenmp. So just two changes to make my code parallel. This is not the best parallel implementation, but it is good enough. So parallel 4 qopenmp. So I recompile, I rerun, and now when I run, this is still very long. Let's see if I really am using parallelism. Yeah, so I'm utilizing all cores, but well, yes, I'm trying to do something cool that's not intended for this lab. As I mentioned, we're not dealing with performance, so I need to figure out what underwater rocks I have. I think the problem here is that I am only running this calculation once, and the overhead for setting up threads is just too high. So if I wanted to see any performance differences, I would probably have to go and modify my application so that I do multiple, I do several, I process several data sets in one offload, because otherwise the offload is too short. But you saw that the runtime at least went back because I shortened the setup stage. So this is the demonstration of the explicit offload model. And this demonstration is supposed to illustrate that A, if you want to use the explicit offload model, you can use pragma offload target mic. Everything inside the scope of this pragma gets offloaded to Z phi. B, if you want to use functions, you have to mark them as offloadable. And the same applies to global variables. C, if you want to use pointer-based data, you have to do data marshalling. You specify what data goes in and what data goes out. And if you want to use to reuse data and or memory buffers, you can use alloc if, free if, combined possibly with some expressions to tell how much data you want to copy. And as I mentioned, pragma offload target mic is only one of the possible offload APIs. There is a similar offload API in OpenMP 4.0, and this is a framework in which you have full control over data traffic, but at the same time you have to implement this data traffic, and you're limited to bitwise copyable arrays. I am ready to go and switch to another lab that demonstrates a different offload API, specifically the shared virtual memory model. And before I do that, let me make a brief pause and look at the questions that have come in. Yeah, the questions are purely organizational, so I'll address them really quickly. Are recorded sessions available? They absolutely are available. And to get the recordings, go to this page, colfaxresearch.com, how 1509, and the recording of the previous session is posted now. The recording of today's sessions will be posted soon. If you don't know how to find this page, go to coldfactsresearch.com, training, web-based, and then you can go to September 7, and this is the page. But there's an even easier way to find this. When you got the invitation to this webinar, the link to this page is actually included in the invitation email. Another question is regarding remote access, and I think this applies to many people who tuned in, so I will address it. The question is, how do I get access to remote system? We have filled up all the seats yesterday, but we have a wait list, and the people who are active, who attend the sessions and specifically ask questions, how do I get access, they will be on the top of the wait list, and after that we will order by the date on which people registered. So if you don't have remote access today, expect a message in the next couple of days, because we will trickle down the wait list pretty soon. And one more question: if you are trying to use your own system, how do you get the Intel compiler? And the answer is that there is a trial version, and I think there are some limited time offers that Intel is running where you buy a discounted Xeon Phi with a longer trial license, or Intel also has academic discounts where you can get Intel compilers at a really low cost, but I'm not the best person to ask about the sales questions. But basically, Intel Parallel Studio XE. This is the site, and you can go to try and buy and download whichever edition you like. Cluster edition has all the tools, professional edition has fewer tools, but it has tuning software. Composer edition has just the compiler. And then Intel has academic pricing and trial licenses. All right, back to the course, back to the exercises. I was now in lab 203, and I think I squeezed everything I could out of this basic offload exercise. So I will go up one level. I want to and one more note before we go there. If you are using your own computer and you don't have these labs, you can download the code from the course page, the same page that you go to download slides, the same page where the videos are posted, and the same page which is included in the invitation email that you get for this webinar. So you can get the code from that page. All right, so I recommend that if you have time, go to this lab 204 asynchronous after the webinar, and this will show you how to deal with asynchronous offload to run something on the host and on Xeon Phi. You can also go to this benchmark offload, which will allow you to see what you have to do to get the best bandwidth of communication. But I will now go to this lab, Shared Virtual Memory Basic, to demonstrate another way to do offload programming. And here in 205, as usual, I have the code and I have a make file. So the make file allows me to compile and run, and it is basically the same application, matrix vector multiplication, running on the host. You can see I'm allocating a matrix, initializing it, and calling the matrix vector multiplication code. Now I want to run it on Xeon Phi, but this time I will try to use the shared virtual memory model. In this model, offload is not initiated with a pragma. Instead, I use the keyword silk offload. So when I try to do that, the first complaint the compiler will have is you're trying to offload this function, but I had no idea that it was supposed to be offloadable. So you had to tell me earlier. So okay, compiler, I go and declare this as an offloadable function. And oh, I apologize. This the correct syntax is first function return type and then silk offload. Well, now let's do it, make it clear. Okay. Oh, yes, I'm thinking too fast. So two keywords. Silk offload initiates offload. Silk shared marks objects and functions as offloadable. So okay, the compiler is now happy with this part, but it is unhappy with the body of the function. It says that I'm trying to use a non-shared global variable in a silk shared context. So it's not happy about the fact that I didn't tell ahead of time that these variables are supposed to be offloadable. So I will put silk shared here, silk shared there, and here I will have to use silk shared twice. Once to indicate that the pointer itself is shared, and the other time to indicate that it is pointing to virtual shared variables. Now the compiler is happy with this function, but it is complaining when I initialize this array, I am claiming that this is just a pointer to an array of doubles. But in fact, this is a shared pointer to an array of doubles. So I have to, this becomes a part of the type of the variable. So now when I compile, it compiles. And when it runs, it seems to be running on Xeon Phi, but I'm still getting errors regarding regarding some illegal accesses to memory. So what is happening now? What's happening is that I allocated data for matrix A on the host. I am trying to use this data on Xeon Phi, but it is not allocated on Xeon Phi, and it is not going to be automatically allocated unless I use a special allocator. And the special allocator reads like that: offload shared malloc. In fact, let me return this, and I will print something out. Let's print address of A on the host. And then I will print address of A on Xeon Phi. Now I have to terminate it. It doesn't even want to terminate. Ah, very good. So I've run into a problem where I'm running an application that just won't stop. So one way to kill it is to try to log into Xeon Phi and then figure out if I can kill anything. So this koi daemon is that's what's hanging. Oh. So I cannot kill it because it's running under a different user. So I could potentially log in as root and kill it, but let me do something else as root. So first let me become root. And I will use a tool from the MPSS toolbox called mic control. Mic control, as you could just see from me scrolling, has options for power control on Xeon Phi, and it also has configuration options. So the option that I want is reboot. I want to reboot Xeon Phi coprocessors, and this will stop the runaway process. So my control-R, and I have to run it as root. It takes a few seconds, but yeah, the process got killed, and now we just have to wait for the processes for the coprocessors to boot. It takes a minute. My control S returns the status, and the status initially is ready, which means that it is trying to load the operating system image. Now it is loading, booting with this operating system image, and soon they will come back online. So one is online, both are online. Okay, so I'm done. So let me run this application again, and this time I will comment out the lines that cause this wild behavior. And so because the pointer itself is shared, the value of A on the host and the value of A on Xeon Phi is the same. But the data behind this pointer are not shared. So what I want to do is I need to use the special allocator offload shared malloc. And when I recompile, you can see that the character of this address has changed. The offload shared malloc returns pointers in a special virtual shared memory address space. And the pages in this virtual memory address space are monitored for changes. So when any changes are detected, the runtime system will synchronize them with the host, with the Xeon Phi, before the start of the offload. And it will synchronize changes made by Xeon Phi with the host at the end of the offload. The granularity of the synchronization is a memory page. This means that if a memory page if one byte in this memory page is modified, the entire memory page will be copied. So it never copies less than one memory page. Okay, so now let me prove to you that all this effort was not in vain and that I can actually run the calculation. Yeah. So now I get correct results. So what I did is an alternative approach to data traffic. As you can see, I did not have to specify anywhere how much data I need to copy. But what I did could effectively be achieved with the explicit offload model. The real utility of this virtual shared memory model is when I'm dealing with complex data structures. And this is what I will demonstrate really quickly in lab number 206. Yes. So just to quickly address once again the question that came in, why is this line printed last? This line is printed last because it was printed into the console on Xeon Phi. And there is a special functionality called a console IO proxy, which buffers everything printed to Xeon Phi and then it copies back on the host. So there may be delays with output coming from Xeon Phi. This is why it's printed last, because it's running on Xeon Phi. So let me now go to lab 206. And here I have a different code. It's basically playing with some data. I have a class. It has a pointer-based variable. It has a method to set this variable. And what I'm doing is I'm making this class a public. I'm declaring a global variable of this class. And then I am modifying this variable on the host, printing the output, and then I'm modifying this on the host again, but I want to prove to you that I can actually work with this class with a pointer-based variable in the virtual shared memory model. So to do this, I'm looking at the clock. The clock shows me that we have only a few minutes left. So instead of doing the modifications live, I will go to solutions and demonstrate the resulting. So yeah, before we go to solutions, let's just run it. So it says, yeah, I should have done that sooner. So this global variable is initialized to null, and then I initialize it with the person is set to Mary, and I print it, and then I set, oh, I'm sorry, this string who is initialized to Mary, and then I modify my class, and I print the result. So yeah, that's what happened. So now let's go to solutions. And see what happened when I made this an application for Xeon Phi with yeah. So that's what happened. I declare my class as not just class person, but as class silk shared person, and then all members of this class, including all methods, also become offloadable. You notice that I allocate my pointer-based arrays using the special allocator, and when I declare this class, well, I declare the pointer to this class as silk shared. And then what happens, this is what's important. This I do on the host, right? I initialize the data of my class on the host. I initialize some other variable on the host. But then, let's ignore this, but then I go to Xeon Phi and I modify my class. And that's what's important. I come back to the CPU and I print the results. So I will make sure that whatever I set on Xeon Phi will be reflected back to the CPU without my involvement. Yes, so the member of the class on Xeon Phi got the word Mary, and when I came back, this string was copied in. So for complex objects, you can use the virtual memory model. And a quick disclaimer that I have is that the overhead of this automatic synchronization may be significant if your offload traffic is significant at all. And so if you're concerned with performance, you have more control in the explicit offload model. If you find this convenient and you want this convenience and you really want to offload complex objects, then you can use the virtual shared memory model. But if your data structures are very complex, then you may be better off just using the native programming as we discussed in session number 1. So what will happen now is I will terminate the webinar, but I will stay online for a few minutes in case anybody has questions they want to ask in the question box. You can do that and I will respond. And if you don't have any questions, then I will see you, oh, wrong slide. Then I will see you tomorrow to talk about vectorization. Thank you very much. See you tomorrow.